I come from IARPA, the intelligence ARPA, or as Wired Magazine calls us, DARPA for spies, or as other journalists call us, sort of the modern day Q branch. Although I wish it were that glamorous, there's no jetpacks in our building or shoe phones. Instead, it's an office building with a lot of research contracts to fund places like Carnegie Mellon to do university-based research. And we do a lot of research crossing broad domains, from neuroscience to computer science, from physics to biology. Because we invest a lot in machine learning, and because we're part of the national security community that is engaged in assessing how advances in machine learning may affect global security, whether through global employment or the development of foreign autonomous weapon systems, or the possibility for large-scale accidents. Because of that combination of ways in which we work on machine learning, I think that IARPA is sort of doubly responsible to be thinking about safety considerations, both because they affect our own work insofar as the results from machine learning systems may influence U.S. policies or U.S. decisions, U.S. actions, but also because we're responsible for assessing how the developments in this technology area affect global security more broadly. So I'm really heartened by the discussions that have taken place here. I think this is really an outstanding event, and my congratulations to Bill and Ed and others here for organizing this. And I'm also really heartened by the public discourse within the research, the policy communities, and the broader science journalist debates about the prospects for safety and reliability being embedded as a key feature of machine learning systems. From IARPA's view, there does need to be more systematic research in safety and reliability. And I think this sort of fourfold treatment of verification, validation, security, and control, and particularly the sort of research roadmap that was summarized yesterday by Dario and gets a longer treatment in the paper Concrete Problems in AI Safety, makes a lot of sense as a place to start thinking about future research investments. One area where IARPA has invested quite a bit over the last several years is in the area of auditability, which I would say is a sort of a weaker form of explainability than the type, say, John was describing, which I think does make sense as the next logical step. But with auditability, something that we require in most of our machine learning research programs is the ability for a system to at least explain how it reached a certain conclusion, to explain that in a way that a human user could understand, and explain it in a way that could be cataloged so that in the future, when you're trying to unwrap how it reached a particular conclusion at one certain state of knowledge about the world, we can look backwards and find out. And that's something that we've now included in, I think, 7 or 8 different research programs in machine learning. And it gets, I should say, successively harder because of the advances in non-kernel-based methods in machine learning that are making the operation of learning itself more opaque, less transparent, as Bill described this morning. So it's something that's making the research harder for us, and I think we need more creative solutions to provide explainability or auditability in our systems. Creative ideas that I hope that some of those here can provide. For national intelligence applications, we also have a special need for understanding the validity of systems with corner cases, with those low probability, high consequence events, catastrophic events like disease pandemics or interstate conflict. Those are events for which, thankfully, we have very few training data. We don't have thousands of examples of global flu pandemics. We only have several, maybe 6 or 7 in the last century that really did reach global proportions. Then inferring what statistical distribution those events are pulled from, whether that's a power law distribution or an exponential, what have you, it becomes much harder just because of the limited data. But it becomes all the more important for national intelligence because it's precisely those kinds of events that national security decision makers are most challenged by. And I would say one distinction between the work that we do in machine learning and intelligence versus that in defense is we're typically operating in intelligence on longer time horizons. The tempo, both of the judgments that we have to make, tends to be slower, but also the optics that we have to use in looking outward tends to be further removed from an event. Because intelligence is really there to support policymakers and other decision makers in planning for events that may take years to unfold. So there again, I think national intelligence applications of machine learning are somewhat distinct from many of the other applications, and we have to take special care then in applying various forms of verification, validation, security, and control. I think another area where national intelligence has special needs in the area of machine learning is in assessing the progress globally in research and development and technology insertion in this area. Not just because we want to understand how the United States competes, but also how we can maintain global security in the face of possible changes to employment, how we can understand advances in weapon systems, and how we can understand the risks of industrial or other accidents from poorly programmed systems. This means, I think, that we need better tools for assessing progress in machine learning. But we also need a set of benchmarks by which we measure breakthroughs. So what are the indicators? What are the milestones that we can agree we've made progress in key problems like sparse learning or transfer learning? I think it would be helpful, at least as one outcome of this sort of national conversation about machine learning, for the research community to understand what should be watching for as indicators of progress, as we have, say, in other technical domains. Lastly, I think understanding the societal impacts of machine learning is really a no-regrets investment. They improve our state of knowledge about machine learning and help us to maximize the benefits from this tremendous opportunity we have right now for advancing this technology while also minimizing the risks. I'll close with a concrete invitation. The first is that this is an area where we do invest both in large-scale research programs that are multi-year, multi-site, but we also invest in smaller studies we call seedlings, which are meant to really help us get from disbelief to doubt on certain hard technical problems. And we fund work that comes to us unsolicited. We're always looking for new ideas that we should be funding, whether that's from a formal institution or from a hobbyist. And the best way of pursuing such funding from us is informally. Is first just to start a conversation with a program manager at IARPA or with me or one of our other senior technical officers. Describe what it is that you want to do and describe how it is that you would measure success in what you do. And my last invitation is to come and do a stint as a program manager. If you're a researcher who has a passion for making progress in this problem of safety and reliability in AI, consider coming to work for government for a few years, work on big problems for small pay, and have a multiplier effect on your research field. I came to IARPA because there were problems in probability theory that I couldn't solve myself, so I wanted to fund 100 people who were smarter than me to solve those problems. And I think places like IARPA and DARPA and HSARPA and ARPA-E, NSF, ASDRNE are great places to have an impact on your research field, to build a new community where one may not have existed. And I think this area in safety and reliability is one where we need more experts in government to join Ed and others. Thank you.